Hi, my name is Olivia Eddy, and here's my presentation on machine learning algorithms for prediction of defibrillator performance. Okay, so a little bit of background for this paper. We know that as technology advances, healthcare, the quality of healthcare and the ease of diagnosis gets easier for the doctors. Medical devices have given better data analysis and control over diagnosis and therapy. And then, for example, like X-rays, let's say you have a patient with a bullet in them. If you don't have an X-ray, then the doctor would have to physically examine. And I imagine that'd be quite painful, especially since you have metal in your body. So it's just comfort of quality of healthcare drastically increased with X-rays. Um, and then medical devices are regulated by organizations such as the FDA. And I know Dr. Lavani and Dr. Kerr have mentioned the Stryker course to help us get a little bit more familiar with the FDA. Due to these, but despite these organizations, medical device incidents are still alarmingly high. This suggests that post-surveillance, supervision mechanisms, and maintenance are not practiced efficiently to prevent malfunctions and maximize patient safety and quality of healthcare. And then this paper focuses on defibrillators. So an example would be like if you have a faulty defibrillator, it could deliver a higher or lower frequency than you need. So this could result in burning the patient or failed resuscitation of the patient, which is obviously not the desired outcome. This study takes place in Bosnia and Herzegovina. Defibrillators are tested in accredited ISO 17020 laboratories. It's estimated that 1% of healthcare institutions' budget is for medical device maintenance and management, but healthcare is kind of run like a business and they have their budgets. So medical device maintenance costs are cut, and this results in an increased rate of incidents. Um, Healthcare institutions try optimizing medical device maintenance, but due to the complexity of the healthcare environment and the complexity of medical devices, these optimized strategies are difficult to execute. And then traditional medical device management consists of software programs that provide updates, increase accuracy, document maintenance history, and data analysis and reports. Okay, prior to this class, I haven't really studied at all machine learning, so I'm not gonna lie, I had to look it up what it is. So here's a video that I found really helpful on YouTube. It's from Oxford Sparks, and it just, in layman's terms, describes what machine learning is.
Our ability to learn and get better at tasks through experience is part of being human. When we're born, we know almost nothing and can do almost nothing for ourselves. But soon, we're learning and becoming more capable every day. But did you know that computers can do the same? Machine learning brings together statistics and computer science to enable computers to learn how to do a given task without being programmed to do so. Just as your brain uses experience to improve at a task, so can computers. Say you need a computer that can tell the difference between a picture of a dog and a picture of a cat. You could begin by feeding it images and telling it, this one's a dog, that one's a cat. A computer programmed to learn will seek statistical patterns within the data that will enable it to recognise a cat or a dog in the future. It might figure out on its own that cats have shorter noses and that dogs come in a larger variety of sizes, and then represent that information numerically, organising it in space. But, crucially, it's the computer, not the programmer, that identifies those patterns and establishes the algorithm by which future data will be sorted. One example of a simple yet highly effective algorithm is to find the optimal line separating cats from dogs. When the computer sees a new picture, it checks which side of the line it falls on and then says either cat or dog. But of course there can be mistakes. The more data the computer receives, the more finely tuned its algorithm becomes, and the more accurate it can be in its predictions. Machine learning is already widely applied. It's the technology behind facial recognition, text and speech recognition, spam filters on your inbox, online shopping or viewing recommendations, credit card fraud detection, and so much more. At the University of Oxford, machine learning researchers are combining statistics and computer science to build algorithms that can solve more complex problems more efficiently, using less computing power. From medical diagnoses to social media, the potential of machine learning to transform our world is truly mind-blowing. To find out more about machine learning, visit oxfordsparks.ox.ac.uk, follow us on Twitter, and find us on Facebook.
Okay, so this article focuses on defibrillators, as seen in the title, but they're going to use machine learning to predict device performance and future failures to optimize current medical device management strategies. Okay, so the methods used, they use 5 different machine learning algorithms. So decision tree, random forest, k-nearest neighbor, support vector machines, and naive Bayes algorithm. I probably butchered that pronunciation. And then the feature selection algorithms are InfoGain, decision tree, and wrapper. The selected algorithms are general representatives from each classifier. And then feature selection algorithms are used to determine which parameters in the dataset is significant to the defibrillator performance. So this optimizes the number of input parameters. So like us, like humans, we have a bunch of not useless information, but just information that doesn't pertain to what we're talking about in the moment. So if that makes sense, it's like brain clutter. So the feature selection algorithms minimize brain clutter, if you will. Data was acquired from 1,221 samples in Bosnia and Herzegovina during annual inspections. The training dataset came from 947 samples, and the testing dataset came from 274 samples. And the samples consisted of 7 features: defibrillator output energy measurements, result of the safety inspection, device age, manufacturer, type, and information about preventative and corrective maintenance and inspection decision. Then each sample had 38 features. There was also an electrical safety inspection that was performed according to the IEC 60601 medical electrical equipment electrical safety standard. So this measured the mains voltage, protective earth resistance, insulation resistance, earth leakage current, enclosure leakage current, and patient applied parts leakage current. And then the inspection decision is either positive or negative. Okay, as mentioned, feature selectors remove irrelevant attributes, so simplifying the model and increasing performance. The InfoGain algorithm is a filter method that ranks features by a score and then computes how much relevant information the attribute gives. The genetic algorithm is a stochastic general search method that is inspired by natural evolution. The genetic algorithm looks at the data set as a population of individuals and selects individuals based on their level of fitness in the domain. The wrapper algorithm is a wrapper method that selects a number of features as a search problem. The algorithm builds a model with a subset of the attributes and evaluates the performance of the model. Okay, so the decision tree has a tree-like structure, hence the name, and the leaves represent outputs and the branches represent the connection between outputs and inputs. The C4.5 decision tree uses gain ratio as a splitting criterion. Pi is the probability that some tuple in partition D belongs to the class Ci. The decision tree is pruned with a confidence factor of 0.25, and then pruning lets the tree be smaller, less complex, and avoids overfitting. Random forest combines multiple trees into a forest, so each tree depends on the value of the vector. Random forest splits data into boxes while minimizing the error at each split. The split between nodes uses the best split between all variables at using the best feature among a random subset of features. Using a random subset of features creates a diverse forest that leads to a better model. In this study, the forest consisted of 20 trees and 6 variables in the random subset. The random forest algorithm is on the right, and parameter mg stands for the margin function, which measures the difference between the average number of votes at random vectors versus the number of votes for any output. K-nearest neighbor is a pattern-based classification method that searches for the nearest training set T. The number of attributes is n, and the closeness of sets is calculated by Euclidean distance, which is modeled on the right. Role factor K is to define the border in the nearest neighbor area. The greater the K value, the smoother the border is between classes. The distance between the test instances and training is computed. So this method is computational and no learning is involved, but this method is suitable for datasets with binary class problems. The support vector machine has two main concepts. It consists of large margin separation and kernel functions. The support vector machine creates a map of inputs in feature space that searches for a hyperplane that maximizes the separation between the two classes. The hyperplane is found using dot product functions, and these are known as kernels. The result of this algorithm is an optimal hyperplane that is represented by few input points called support vectors. The naive Bayes algorithm is a probabilistic classifier based off of Bayes' rule. So on the right, there's the equation pH is the independent probability of the hypothesis. So this is also referred to as the prior probability. PD is the independent probability of the data. PDH is the conditional probability of D given the H. This is known as the likelihood. And then PhD, it's not a doctorate, is the conditional probability of H given the D, which is also known as the posterior probability. Okay, so here's a visual of how the data is processed. So the raw data goes through dataset analysis. So that would be where the feature selection processes are. So like the info gain, the genetic, and the wrapper algorithms. And there's also a group with no feature selection, so like the control group. And then it passes that information, once it gets filtered, gets passed down to the system development. So that's where the machine learning algorithms are. And then the output of the whole model would be the performance status prediction. So the performance evaluation, so we're testing the prediction created by the machine algorithm, is evaluated by the true positive rate, the true negative rate, the false positive rate, the false negative rate, and accuracy and precision. And then the equations for accuracy and precision are shown on the right. Okay, so the results of this experiment: the info gain selector for decision tree, random forest, K nearest neighbor, and support vector did not change when compared to using all features, so the control. The genetic algorithm was best for the random forest with accuracy of 100%. The wrapper algorithm was best for K nearest neighbor and random forest. Overall, the random forest machine algorithm was the best prediction and classification accuracy for all feature selectors. Overall, random forest paired with genetic algorithm feature selector gave the best prediction and classification accuracy. The accuracy also depends on other factors such as precision of the measurements, subjective physical examination of the device, so again, human error, and the division of training and testing datasets. In conclusion, machine learning can be used to assess the state of medical devices. This, in turn, can help medical institutions determine what machines need maintenance and prevents machines that need maintenance or faulty machines from being used by the medical professionals. Having properly maintained equipment allows us to reduce the number of medical device-related incidents and provide patients with better quality care.